Today we're going to talk about independent events and conditional probability. First, let's introduce the concept of relative frequency. Relative frequency is when you use the outcomes of a smaller experiment to make assumptions for a larger population. Pause the video so you can write down the definition. So for instance, let's say you asked 40 people what their favorite flavor of ice cream was, and 8 of those 40 people said chocolate. So that gives me a 20% probability, right? 20% of the people said that chocolate was their favorite flavor of ice cream. So relative frequency says that I can take that number and perhaps for the whole United States, I can estimate that 20% of the people in the United States have chocolate ice cream as their favorite flavor. Now, there's a problem, right, when using relative frequency. 40 people were not a very big sample, right? So we need to be careful when using relative frequency because testing a small sample of people will not give you accurate results. You need to choose a lot of people to test and choose those people at random to be able to use the results and say they're accurate. A biased sample is when you don't choose the people at random. Let's say you only chose people who you saw eating chocolate ice cream. That would be a problem. You need to just randomly pick people to ask, and you need to choose a lot of people to ask in order to make it accurate. So in other words, a small sample or a biased sample gives us unreliable results. A larger sample that's chosen at random gives me more accurate results. So 8 out of 40 giving me 20%, not a very reliable estimate. If I chose 4,000 people at random though, and 600 of those people said they liked chocolate best, then I could assume that about 15% of the overall population would like chocolate ice cream best. Remember though that this is only a prediction. It's not guaranteed to be the actual number. I can't actually say that 15% of the whole United States likes chocolate ice cream better than any other flavor. But sometimes it's the best we can do, since actually asking the entire population of the United States would be virtually impossible. In probability, events are either dependent or independent. We're going to define those next. An independent event is one where the occurrence or non-occurrence, right, it either happens or doesn't happen, of one event doesn't affect another. So let me give you some examples. If I roll one die, that die is not going to have any effect on what another die does when I roll it, right? One die doesn't affect another. Or if I spun a spinner and flipped a coin, they wouldn't affect each other, right? Spinning the spinner doesn't do anything to what the coin's going to give me, right? It's still going to be heads or tails. And spinning and flipping the coin won't affect what I get as a spinner result. And you eating your favorite flavor of ice cream won't affect what another person's favorite flavor is going to be. Those are all independent events. Dependent events are ones where the outcome of one event affects the outcome of another. So let me give you some examples for those. If I draw a card and don't replace it in the deck, the next time I draw a card, there's no way that I can draw that same card again. So the outcome of my second event has been changed. If I take a sock out of my sock drawer and don't put it back in, it's going to change the number of socks that I can choose from the next time I need to choose a sock. And if you have 5 yogurts in the fridge and you eat one and don't replace it, the next time you pick a yogurt, you're only going to have 4 yogurts left to choose from instead of 5. These are dependent events because the second event won't be exactly the same as the first. They're going to have different probabilities. So let's take a look at conditional probability. Conditional probability is really similar to the probability you already know, except we're going to put conditions on the sample space. We're actually going to change the sample space. So let's take a look at our rolling 2 dice chart. Let's say that I wanted to find the probability of rolling a sum of 8. So when we looked at this before, out of all 36 results or possible outcomes, 5 of those gave me a sum of 8. So my probability was 5 over 36, or 0.14. There are 14% of these 36 outcomes that give me a sum of 8. So now let's change it up a little bit. Let's say I wanted the probability of getting a sum of 8 if I already rolled a 3 with the first die. The second part of this sentence is a guaranteed part of our experiment. So that's going to change our sample space. If I look at all the outcomes where 3 is the first number, I only have these 6 possible outcomes. So my sample space just went from having 36 possibilities to only 6. If I look at those 6 possibilities and which ones give me a sum of 8, there's only 1. So this means that my probability, instead of being 5 out of 36, is now 1 out of 6, which gives me a 0.17 probability. Not a huge change in the overall scheme of things, but enough to make a difference. Sometimes with conditional probability, our probability is going to change a little, and sometimes it's going to change a lot. It's going to be really significant. This all happens when I change the size of the sample space. So let's look at the definition for conditional probability. In notation, this is what a conditional probability is going to look like. I would read this: the probability of B given A. That means that I'm looking for the probability of B, the probability that B occurs, given that event A has already occurred. We already know that event A has happened, and that's going to help us change our sample space. Here's the official definition. Conditional probability of B given A is equal to the probability of A and B, in other words, the intersection of A and B, over just the probability of A. Probability of A is how many events are in set A. So let's go back to our 2 dice chart. Let's say that we want to find the probability that both numbers are odd if their sum is 6. So the second part of our sentence is what's going to help us change our sample space. We're going to only look at outcomes whose sum is 6. So let's take a look at these really quick. First, how many numbers do we have where both numbers are odd? Or how many outcomes do we have where both numbers are odd? That's going to be event A. Then, how many do we have? How many outcomes do we have where the sum is 6? And we have 5 of those, and we're going to call that event B. So notice I'm looking for the probability of event A when event B has already happened. So now, instead of using all 36 outcomes, let me get to the next page. This is what it's going to look like. I want the probability that both numbers are odd, given that I already know their sum is 6. So I do the probability of the intersection over the probability of just B. In other words, if I want to go the long way to get there, the intersection has 3 out of 36. right? The 3 spaces where I have yellow and purple. And the probability of B, the probability of a sum of 6, is 5 out of 36. If I simplify that fraction, I simply get 3 out of 5. So here's another way to look at it. I look at the intersection. I have 3 spots that have both to be true. They have both numbers are odd and their sum is 6. Out of how many have a sum of 6? Only 5. So out of the 5 spaces where the sum is 6, only 3 of them have both numbers that are odd. Make sure to write down any questions that you have. We'll go through some more examples in class so that we can really cement down conditional probability. But make sure that you take the online quiz and bring your notes to class so we can add to them. Have a great day, and I'll see you later.